All right, surface area of prisms, and hopefully that will segue into talking about surface area of cylinders. And then hopefully by the end of the period we get into a more authentic type problem that we would be interested in regards to surface area. Okay. So yesterday we stopped here. I would like to continue this one and finish off this surface area of this triangular prism. Yesterday we laid out this formula that said surface area is going to be your lateral area plus two bases. That's kind of a static or unchanging formula for all prisms. Okay? But at the same time, it's dynamic because this lateral area, which it's always going to be pH. That lateral area, depending on what my base is, P might be found by the perimeter of a triangle, it might be the perimeter of a rectangle, it might be the perimeter of a hexagon, whatever. Okay? But this capital B here, that is where it's more dynamic, because if it's a triangular prism, that B, like we said yesterday, is 1/2 base times height. If we look at this picture here, that B would be, we'd probably actually have to section this off and actually come up with an irregular shape because that's not a regular pentagon. So we would have to maybe do some scratch work on the side to actually find out what that orange area is. If we came up to, let me scroll down here, this one, that's a hexagon. Okay, so it's going to be 1/2 AP is what capital B is going to be. This is an octagon. It's going to still be 1/2 AP, but the way that we go by finding A and P will be a little bit different in that one. So the idea is as we progress through different shapes here, that's a trapezoid, so it would be 1/2 H times the sum of B1 and B2. Okay, so capital B changes per the shape we're dealing with. Okay, so that's something always to think about. So if we're trying to do this, what we need to understand is that not always will we have all the values we need. If P stands for the perimeter of the base, I need to realize that the base here is going to be my triangle. I've got 3, I've got 4. They tell me this is a right angle right there. So what can I use to find that distance right there? Pythagorean theorem. And what is that distance going to be? 5. Okay, so when I do my perimeter here, okay, 5, 4, 3 adds up to 12, right? So my perimeter is 12. Okay, now H is the what? It's the height of, okay, so correct. Yes, so we refer to that as H for the prism. Okay, it's the distance between the two bases. Okay, so that would be 6. Is it okay with everybody? So what that does, 12 times 6, what that does, and you can do this on your own if you'd like to, but it's going to find that area right there of that rectangle, which would be 3 by 6, right? Okay, so 3 by 6 would give me what, 18? Okay. If we take this rectangle right here, that'd be 4 by 6, so 24. If we take this rectangle right here in front of us, that'd be 5 times 6, which would be 30, right? Add those all up. What's 8 plus 4 plus 0? Carry the 1, right? 3 plus 2 plus 1 plus 1? 7, right? What's 12 times 6? You see how that's more efficient? Okay. I don't care how you do it, but if we're on a test and a quiz, and I take those tests and quizzes and I make them the size that I think they should in regards to the time that it should take you if you use the most efficient route, you'll probably finish that test or quiz if you use P times H. You might not finish if you go through and you find every individual area and add every individual area. Okay. We're now going to add to it 2 of our bases. So I'm going to go 1/2. Now, when I'm looking at the base, I am now just focused only on this shape right here. Okay. So what can I use as lowercase b on this blue triangle? Can I use 3 as the base? Because remember, the base is defined by where your altitude, I guess let's phrase it this way. Your base is defined by what altitude you use. So if I'm going to use 4 as my altitude because it meets that definition, that it's perpendicular to, it starts at a vertex and goes perpendicular to the opposite side. If 4 is going to be my altitude, then 3 would be my base, right? But for the same reasoning, this segment here starts at a vertex and goes perpendicular to the opposite side, or the line containing the opposite side. So could 3 also be called an altitude? So then 4 would be the base, right? Could we, now I don't know that anybody would do this because it would be kind of silly. Could I use that distance right there? Because it starts at a vertex and goes perpendicular to the opposite side. That could be my altitude, and that could be my base, right? So inside the triangle, there's 3 different ways, 3 different groupings of B's and H's that you could use, but no matter what you use, you should get the same area. Does that make sense? Okay. This one here would be hard to find. We could probably do it, but there's no need to. I'm going to use that as my base, and then 4 would be the H. And yesterday we talked about this, just to remember, that H right there and that H right there, they are different. This one's for the prism, and this one's for the base of the prism. Okay? So that's always something that you got to be leery of. What's going to happen with this 2 and this 1/2? Cancel out, and I got 3 times 4, which is 12. 84 square centimeters, right? What if I asked you to convert that into square millimeters? Anybody remember how to do that? Okay, so let's kind of think about this. I think we talked about King Henry died by, and that's your base, right? Drinking chocolate milk, correct? So this is kilo, this is hecta, this is deca, this is your base, this is deci, centi, milli, okay? Now we can, so this would be 10 to the 0 if we're talking about like decimal places. This would be 10 to the -1. This is 10 to the -2, 10 to the -3. This will be 10 to the first. This will be 10 squared. This will be 10 cubed. Okay. Which basically means, so 10 to the 0. What's 10 to the 0? Careful. It's 1. Okay. That's why it's referred to as our base or our unit. Okay. Because of that 1. 10 to the third is 1,000. So basically what we're saying here, okay, so that'd be 1,000, that'd be 100, that'd be 10. This is 0.1, 0.01, 0.001, okay, or 1 out of 10, 1 out of 100, 1 out of 1,000, okay. That's what this is. So if I have 1 kilogram, that means that I actually have 1,000 of these grams. Does that make sense? If I have 1 hecta, maybe, let's say I have 1 hectometer, okay? That means I have 100 of these meters. Is that okay with everybody? Okay. So right now, we have an answer that is it's 84 centimeters squared. Okay. remember what we do here. So if I had, let's just say I had 84 centimeters. 84 centimeters. So I'd be right here, 84 centimeters. So my decimal point would be right there, correct? Wherever I want to go on this sliding scale, I just have to count from where I'm currently stationed to where I want to go. So let's say I want to go to milliliters. That's only, or sorry, millimeters. That's only 1 unit to the right, correct? So that movement from here to there tells me I need to move that 1 unit to the right. Well, if I need to go 1 unit to the right, then I need to put that there, right? So if I started with 84 centimeters, that converts to 840 millimeters. Is that okay with everybody? Okay. So does that make this go to 840 millimeters squared? It does not. Okay, and here's the reason. And we dealt with this, and this is where I think there is a disconnect between what you do in science class and what we do here. So in science class, you're not dealing with areas ever. Okay? And if you're dealing with volumes, the volume that you deal with is not cubic centimeters, it's milliliters, which is an equivalent comparison of the same thing. 1 milliliter is equal to 1 cubic centimeter. But because you do that in milliliters in that unit, you don't think about what is happening when we actually do the conversion. If I have 800 or 84 centimeters squared, okay, what that means is I have 84 centimeters times centimeters. Does that make sense? Okay. Meaning over here, think about this. When you did P times H, and it happened over here as well, but when you did P times H, you did P was 12 centimeters, right? Okay. And when you did H, it was 6 centimeters. So you had 12 centimeters times 6 centimeters. And that would give you 72 centimeters, right? Same thing here. This would have been centimeters and centimeters. So you got 3 centimeters times 4 centimeters is 12 centimeters. So we get 84 centimeters. Well, if I want to do conversions, and I want to get this thing into millimeters squared, okay, what you need to do is you need to get this centimeters to cancel with a centimeter. Does that make sense? And there's a ratio that for every 1 centimeter, there are 10 millimeters. So if I multiply that out, what that's going to do is that's going to move the decimal place 1 spot to the right. But my units that I would have left over are centimeters, millimeters now, because those canceled, right? To get this centimeter to cancel, I need another one here. So this is going to move my decimal place. So I multiply by ultimately 100 here. Excuse me. That's going to take the 84.0. It's going to move it to a 1. That one right there moves it 1 to the right. This one right here moves it 1 more to the right. So 804 or 84 centimeters squared does not equal 840 millimeters squared. 84 centimeters squared equals 8,400 millimeters squared. Does that make sense? Okay. Now, think about this. The reason you do this, if you wanted to change this into millimeters, how would you change that into millimeters? Because that's now first degree, correct? Yeah, you would move your decimal place 1 spot. So this is going to contribute to moving decimal place 1 spot and gives me 120 now millimeters, right? How many units would you change? How many decimal places would you move that to the right to get to millimeters? 1, so you get 60 millimeters, right? This one here would have been 3 centimeters. That would have been 4 centimeters. How do you get them to move to the right to millimeters? It'd be 30, right? That moves 1 to the right. This would be moved 1 to the right, and that would give me 40. Okay? This is going to give me 7200. This one here is going to give me 1200. Add those together, what do you get? 8400. Okay? So, because it's a two-dimensional, area is a two-dimensional value, right? Or concept. When you do conversions, that means you need to convert both those dimensions. This right here, King Henry died by drinking chocolate milk, the way you've always learned it is a first-degree conversion tool. Okay? You can still use it for second degree. Okay? Think about this. If I moved 1 here, okay, but this was squared, all I've got to do is move it, that 1 times that power of 2. So just double it. Does that make sense? So I moved once on the sliding scale, double it, and that really tells me how many I got to move my decimal place. So let's do this. Let's say we started in centimeters squared. Let's go 84 centimeters squared, and we want to go to kilometers. Okay, that equals how many kilometers squared? Okay, well, because I'm in centimeters squared, I'm going to start there, and I'm going to say, okay, I need to move 1, 2, 3, 4, 5 decimal places, right? 5 decimal places would transfer a linear centimeter to a linear kilometer. But we need to do that twice, right? So how many times do I really have to move my decimal place? 10 spots. So I'm going to have 0.00000000084. And a lot of times they write that as 8.4 times 10 to the, how can I write this in scientific notation? Negative, well, 1, 2, 3, 4, 5, 6, 7, 8, 9. Always put it between the 8 and the 4. Kilometers squared. So if you want to use King Henry, that's always an issue. Okay, that's why I want to talk about this. When you want to use King Henry died by drinking chocolate milk to make conversions, that's fine. First degree, all you got to do, if I'm going centimeters to millimeters, centimeters to kilometers, whatever, I just count how many spaces I moved over. If it's squared units, I count how many spaces I moved over, and then I double that, and that's really how many I move. Does that make sense? If it's cubed, so we're talking about volumes now, what would you do? Multiply by 3, because now you got 3 dimensions that need to change, each into the same unit. So that would be 3 times moving across that scale. So just be careful with that as you answer questions, because eventually that's what we're going to get into. That's a lot of what the next 2.5, 3 weeks are going to be, is us finding a surface area, finding a volume, and then taking that number and manipulating it to maybe find something else, maybe to find a cost, maybe to find a surface area or a volume in a different unit. So we're going to have to do some conversions. Okay. Here's another one. Okay, so this is well, what would you call this? What is going to be your base? The hexagon. Okay, so this would be a hexagonal or hexagonal prism. Okay, but that is going to be my base. Okay, so let's go ahead and find the lateral area first. So the lateral area, remember, is P times H, correct? Okay. What's the perimeter of this hexagon? 36. What's the altitude of the prism? 12. Okay, what's 36 times 10? 360. What's 36 times 2? 72. What's 360 plus 72? 432. Okay? So my hope is that you realize that that is much more efficient. Okay? So that area right now of the lateral area is 432 square meters. That is quicker than finding that area, and then finding that area, and then finding that area, and then finding the other 3, right? Okay, now some people say, well, Mr. Fay, I can be more efficient, and I can just say, well, one of those rectangles, because this is a regular polygon, it's a regular hexagon, that one of those rectangles is the same as the other 6, right? So if you want to go 12 times 6, which would be, careful, 72. Take 72 times 6 then. Okay, if I look at 36 times 12 and 72 times 6, they're the same thing. I'll still get 432. So you can use either approach here. I like this one because the next thing I'm going to have to do is find the area of the base, which, if you guys remember, the area of the base for a regular polygon is 1/2 AP. Does anybody remember what P stood for in that formula? Perimeter. Using this tool here, this technique here, do I know that number? 36, right? Where if I would have just found the area of that rectangle multiplied by 6, I don't necessarily have that easily available to me, and I got to go back and do that extra calculation. So I know P is 36. I've got 1/2. Now we got to find the apothem. If you remember the apothem, it is that distance right there. Okay. Now that I'm going to draw the hexagon, or part of the hexagon right here. So that's my apothem right there. Okay. This distance here is 6, right? Anybody remember what that distance right there is? 3. Okay, it always cuts it in half, right? The apothem always cuts that in half. I don't know A. Does anybody remember how I find that angle? (360) divided by 2n. Because n is the number of, well, it is the number of sides, but n is, so number of sides, but it's also the number, because of the number of sides and because of the number of vertices, it's the number of those triangles that can be fit into that hexagon, right? So if I take 360 and divide it by n, that gives me that vertex angle, that black triangle, to be 60, but I only want half of that, so cut that 60 in half again, and it's going to give me 30, right? Yes, so that's why I said 2n here. So instead of cutting it, taking 360 and cut it up by 6s and then cut by 2, well, that's collectively cutting up by 12s, right? We're dividing by 12. So that's why we divide by 2n. But that gives me 30. So now if that's 30, what's across from 30? What side is that? That's your n side, right? Isn't this going to be 2n? And your apothem in radical 3. Remember doing that? So now I know my apothem. It's 3 radical 3. Okay. So what would be 2 bases? Huh? Well, the 2 and the 1/2 are going to cancel, right? So 2b would be 2 times 1/2 times 3 radical 3 times 36. And the 2 and the 1/2 cancel. So now what's 3 times 36? 108. So I have 108 radical 3. That is what 2b is equal to. Okay, so remember, surface area is lateral area plus 2 bases. Our lateral area was 432. Our 2 bases are 108 radical 3. And this would be meters squared. Can I combine these? No. Cannot add, unlike radicals. Can't add a rational number to an irrational number and get a rational. Can we do that? All right. So I'm going to skip this one for now, but let's at least write the formula down here. Okay. If I want to find lateral area again is P times H, right? If I want to find B, does anybody remember? So what is my base here? What's the... Okay, so the trapezoid here is your base, right? So we got to find that area formula. So if you can't recall this stuff, guys, I have no problem with you doing a quick Google search saying, hey, what's the area formula for a trapezoid? Okay. Now, when you do that, just be aware that some shapes have different area formula. If you type in area formula for a hexagon, there are different formulas than 1/2 AP. Okay. 1/2 AP is the one that we use because it can then be used for a hexagon, an octagon, a pentagon, whatever. But there are other formulas. So if you see one that you think, oh, that's something I've never dealt with, search something else. Does that make sense? But the formula for a trapezoid is 1/2 H times B1 plus B2. Okay, now just think, what is this H right here for lateral area? Right, so for the height of our prism is going to be 10 centimeters, right? What is H here for the base? That's 4 centimeters. Is everybody on the same page with that? Okay. I think that's the biggest, that's the reason I got this question on here, is because I want to make sure that we understand that there is a difference between the H's that we use. Okay. Skip that. Skip that. What if I took, so let's say, let's see this, we do this in GeoGebra real quick. That, and let's put up this. How can I do this? Give me the visual that I want you guys to see, but what if I took, so I'm going to take this shape here. I'm going to ask it to show it as the base in the three-dimensional plane. Okay, let's get rid of the grid, the plane, and the axes. Okay, so zoom in there. So I'm going to take this base, and now I'm going to come over here and just create an altitude of, I don't know, let's say 7. So it creates that, maybe that altitude is a little bit much. Okay. So it extrudes it. You guys ever play with Play-Doh? And you got those little machines that you push down. You put Play-Doh in like the hopper and you push down and it shoots out like spaghetti. That's called extruding. And that's really what's going on here. So we take our base and it becomes a triangular prism. Now, I'm going to take that base and I'm going to make it now go to a rectangle, but it's a square because like I've forced this to be a regular polygon, so that's a square rectangular prism. Make it a pentagonal. Okay. So what's going to happen here? What is it? What shape? And then I got to zoom out to really get a good. I want this to be confined to an area as I change so I had to do a little bit of formatting here to get to do what I really want to do. But in terms of time constraints right now, I'm not going to do it. I'd like this shape as I add sides to it just to stay kind of in this area. Does that make sense? But as I add sides to this thing, okay, we go from what's that, an octagonal? Okay, then we go to a decagonal. So that'd be a decagon as my base. The more and more sides I add, the more and more sides that I add, the base is going to be a circle, right? Okay, let me get rid of these labels. Okay, but what is this shape over here turning into? Cylinder. Okay, so what I'm trying to get at here is the more and more sides that we add to our regular polygon, and this is what I was trying to constrict the X and Y axes that this regular polygon was being built on, okay? But what happens is that these sides here become smaller and smaller and smaller the more sides that I add. Does that make sense? Each one is smaller and smaller. So eventually, it turns into a circle. If I have an infinite number of sides on that shape, that polygon turns into a circle. Well, then, if we extrude that circle, we now get, instead of a prism, we get a cylinder. Okay? So now here's the question. What would be the formula for a cylinder? Is there any difference? Because the idea is, let's say we knew infinity, just to make this a little bit easier. Let's say we knew what number infinity was. Let's say we thought infinity was 100 sides, okay, or the number 100, okay? So the 99 would not be infinity, correct? Okay? So if 99 is not infinity, and I had then 99 sides, then I would have a 99gon as my base, and my three-dimensional shape in red on the right would be a rectangular prism with 99 sides. Does that make sense? But once I go to 100 then, now I have essentially infinite sides on the left, and now I would not have a prism on the right. Does that make sense? I would have a cylinder. So the argument is, where is that transition? Because we don't know what infinity is. It's not 100. So where does that transition of having a rectangular prism convert over to a cylinder? Okay, that it happens at infinity. It happens essentially when the width of each one of these rectangles in here. Okay, so if I look at that blue rectangle, okay, if I can make that blue rectangle infinitesimally small in regards to its width, and that's what we talk about in calculus. Okay, if we make that blue rectangle infinitesimally small in regards to its width, and then do that with every other rectangle up there, we'll get a smooth surface. Does that make sense? Okay, and it will be our cylinder. But the transition from being a rectangular prism to being a cylinder is very, very small transition, meaning that if right now at 100, or let's put it back to 99. Can't get there. Let's say at 99, this is still considered a rectangular prism. Okay? But at 100, if 100 is infinity, now this is a cylinder. Did that blue rectangle is different when that's at 99 than it is when it's 100. But is it much different? No. Okay? So then the surface area of the prism at 99 cannot be much different than the surface area of the cylinder when we get to 100. Does that make sense? So what I'm trying to argue here is because of calculus and a concept called limits, which is why that's kind of a hard topic to discuss because you guys don't know what limits are yet, is that if I want to find the area, the total area, or surface area for a cylinder, it is still lateral area plus 2 bases. It's the same exact formula, okay? However, it's probably never, ever presented that way to you, okay? Because think about what lateral area was. Lateral area was perimeter times height, right? Okay? Plus our 2b, and I'm just going to put parentheses right now for that, okay? Okay, well, be careful, okay, because we're not talking about okay. So you for B, okay. Let's go back to perimeter. What is perimeter for a? So our base, right? That's what we're doing here. The lateral area, that P, is the perimeter of your base. In a cylinder, what's your base? A circle. What's the perimeter of a circle? The circumference. So it's 2 pi r. H is still H. It's still the altitude of your cylinder. Does that make sense? It's the distance between the two circles now. And you said that B was the area of your base, which your base is now a circle, right? So what's in those parentheses would be pi r squared. So that is generally the formula that they give you for finding the surface area of a cylinder, 2 pi r h plus 2 pi r squared. But what I want you to understand, it's the same thing as the surface area of a prism, because a cylinder is the morphine of a rectangular prism, right? When the sides get infinitely many. Another way of visualizing this is to do something like this, okay? So I've got this cylinder over here, okay? If I take that top off, take that bottom off, okay? So I've taken like a can opener, take top and bottom off, right? Okay? Then take a pair of like 10 snips and slice straight down that line right there. And then start unfolding it, okay? And unfold it flat. I get that, right? Okay? Was this distance right here, was that distance the height of your cylinder? Okay? So that was H. That's kind of hard to see. Let me zoom in on this. Okay, so that was H. Okay? Now, we know that this would be pi r squared, correct? R is the radius that they're showing me there. So that would be pi r squared, and this would be another pi r squared. So there's 2 pi r squareds, correct? Now, let's talk about this blue area. How would I find that blue area? Well, think about how long this distance right here would be. Just wrapping it back around, isn't that distance right here across that edge of that rectangle, isn't that what matches up to the circumference of the circle? So this is H, but this would be the circumference of the circle. This would be 2 pi r. Does that make sense? Okay. Well, how if that distance is 2 pi r and that's H, how do I find the area of the blue? 2 pi r times H, right? 2 pi r times H plus 2 pi r squareds, okay, 2 pi r H, okay, which would be the area of the blue, and then 2 pi r squareds would be the area of the circles. That kind of make sense? Okay, so there's a couple different ways you can visualize where that formula comes from. We can have cylinders that are right cylinders. Those are the ones where the two circles are directly on top of one another. There's a line segment from one center of one circle to the other, and that line is perpendicular to both circles then. Okay, so what I mean by that, and this is the way that we would check to see if something is right, if a cylinder is right, is that that's the center of the top, that's the center of the bottom. If we connect those and it's perpendicular to both of them, then we would say that this is a right cylinder. Okay? You see here that if I connected those, if I drew a line down perpendicular from that top one to the bottom circle, that line does not touch both centers, right? So that cylinder would be oblique. Okay? Leaning Tower of Pisa, oblique cylinder. Okay? Or we can view it, if you really get down, discuss it, it's not the way it's built. So basically what happened was Leaning Tower of Pisa built as a right cylinder, essentially, right? Ground starts to give way over here, okay? So now Leaning Tower of Pisa looks like this, where the ground is like right there. Does that make sense? So is it really an oblique cylinder, or is it just still a right cylinder with half of it buried in the ground, right? Okay, so you see questions like that every once in a while talking about the Leaning Tower of Pisa in a story problem. It's really not an oblique cylinder, okay, because still connect that center with that center. Huh? When I was there, you could not go in it. You could go around it. I don't remember if there was I don't know if they were remodeling it or doing updates on it, but all right. So what I want to do, I'm not going to spend a whole lot of time on these examples with you. I think you guys can figure out the R and the H's that need to be plugged into that formula and these basic questions. I want to come down here to this question. And actually, let's stop. We'll start that tomorrow. Okay? We'll stop today. There's an assignment in Math Excel. It gets you kind of the ball rolling with these formulas of finding surface area of prisms and cylinders. So because we didn't do too many cylinder questions, specific questions, maybe once we hit those tomorrow, give me an idea of whether we need to do some of those basic ones or not. But I'd really like to jump into this one because it's more, I think, higher level thinking, which I think we're capable of doing and we need to be doing, other than the ones that maybe we see in the text. So that assignment's open, and we'll talk about some of those questions tomorrow, but start with this one specifically tomorrow.